Now, it's my pleasure this morning to introduce Stan Williams. Okay, Stan does not really need any introduction in this audience. Anyway, I will read a few lines. Okay, I took from the internet. He served as a professor in UCLA since 1980 until 1995. Then he joined HP Labs as director of the Information and Quantum Systems Lab. And he's most famous for introducing the memristor that we all know, and gives the name to this name and inspiration to this conference and a whole community that we belong to. Most recently, since 2019, he's back to academia in the Texas A&M University. Today, Stan will give the talk about the connections among edge and chaos, excitability, and thermodynamic efficiency in memristors. So let's give a handful of welcome to Stan.
Thank you. What I'm going to talk about today are a bunch of different things. I've got a clock here that I'm going to try to read, although there's a light shining right in my eyes. So I'll see if I can figure, I don't want to go on too long. But really, when I came up with the title for this, I didn't know what I was going to say. And it was in putting together the talk itself that several different things that I've been thinking about for years started to really fall into place. And so this will be the first time I've really tried to tell people about this. And I think it's hopefully going to be worthwhile. So, of course, I have a large number of people to acknowledge in terms of all of the wonderful interactions that I've had with and learnings that I've had over the years, most especially Leon. But I want to say something very explicit, and that is that any mistakes are mine. Okay? If I screw up, it's me screwing up and not somebody else. All right. What are we going to look for in this presentation? Instead of an outline, I'm going to give you some hints of some things that I'm going to be talking about. And when you see them, you'll say, oh, okay, I've seen that before. And so the hints are, I'm going to be talking about entropy production minimization, and whatever the heck that is. And it's going to involve a branch which is now called stochastic thermodynamics. This used to be non-equilibrium, but thermodynamics has undergone a revolution of its own and has a completely new formulation, if you will, which is called stochastic thermodynamics, and that's important for this talk. I'm going to talk about Brian K. Ridley and what I call a Ridley transition. And what that means is when you have something that has negative differential resistance, if that NDR is steep enough, the voltage, but also the power in a circuit decreases. And so you're actually improving the power dissipation in a circuit when you increase the current flowing. And you actually, what I'm going to try to convince you is that you actually reach a point of optimal thermodynamic efficiency. In other words, when you are in a system that is operating at edge of chaos, it is also optimally thermodynamic efficient. You can't get any better. But those two things are almost independent of each other. They just coincide. So then an edge of chaos. Of course, this is from the realm of nonlinear dynamics. And what I want to do is I want to talk something about Chua, what I'll call Chua excitability. This is something that's very important. It's mentioned quite a bit, but it's been described in words. And what I want to do is I want to show it to you viscerally. I want to show you a measurement of excitability so that you can get a feel for what that means. And then we have this issue of complexity and adaptability. So first of all, let's just take a look at the field in large scale. Everyone knows about the memristor, but really the memristor is just this tiny little thing poking up above the surface of the water. It's what alerted most of us to the fact that there was something here. What's really going on in terms of trying to understand what we can do with memristors and in electronics is the fact that this is within the field of nonlinear dynamics, which is critical. You need to understand local activity, what that means in terms of how a memristor functions. And then, of course, there is this magic edge of chaos that you've already heard about a couple of times, which only took me 17 years to understand. I first read the paper about edge of chaos in the early 2000s, and it wasn't until something like 2022 that I finally understood it and convinced Leon that I did. I went over to his house. I was so proud of myself. And he gave me a quiz and said, yeah, okay, yeah, you understand it. But nobody else in this audience has done that, have you? Okay? Well, there's a couple of people here that know it. But so this is what I'm going to try to do is distill a lot of this and tell you about it. But there's actually something even bigger here. This is all important. But the iceberg is floating in the ocean. And what the ocean represents in this case is thermodynamics. It's the sea of stochastic thermodynamics. And so the fact that you have all of this here actually relies on thermodynamics for anything to happen at all. Without the thermodynamics, nothing else works. That's what I'm going to try to show you. And what's important is what's called entropy production and entropy flow, and that's what stochastic thermodynamics is all about. So why has the rate of progress in nonlinear dynamics been so slow? 1971, Leon invents the memristor, publishes a paper on it. 37 years later, I publish my little paper. A gap of 37 years. During that 37 years, Leon's original paper was cited in the literature 7 times. Last year, there were a total of 80,000 citations containing the word memristor in 1 year. So obviously there was something funky going on, right? There was this long delay. And what I'm saying is it's mainly a failure to communicate. Why was the progress in linear dynamics so slow? Well, the math is absolutely elegant. But the problem is it doesn't matter how good the math is if nobody understands it. If you have an audience of 3 or 4 in the world, it's not going to go very far. And so if the math is too abstract for experimentalists to understand, it's not going to go anywhere. If there's no physics that implements it, well, many people thought that was the case. For the memristor, people thought that it was just a toy model that had no existence in this universe. And this is not unusual. You can have a mathematical formulation which is correct, like string theory, but it has no relevance to anything real. And that's what people thought for most of 37 years about the memristor. It was cute, but not real. There's other physics that interferes or prevents it. It could be true, but there could be something else that masks the whole thing. Or, as I'm going to show you, entropy production minimization, which takes it and enhances it and makes it bigger than it would be otherwise. Here's a big one. No existing instruments that can measure it. The vast majority of the measurements that people are making right now on memristors are giving not very good data. I won't exactly call it garbage, but it's not the greatest. And it's nothing that you can actually use intelligently to try to understand your system. And so when you're working in this area, literally, you either have to take your instruments and just calibrate it like crazy, or you build your own. And that's what I've had to do, build my own. And several other groups have figured this out as well, and they do that. And then, of course, there's a final issue, and that is all of this can be completely moot if the noise in whatever circuits that you're measuring is so large that it just masks all of the effects that you're trying to show. And what I'll say is that over the past many decades, all of these things have been true at one point in time or another, or people thought they were true. Now, I was inspired when I went to the National Museum of Scotland the other day and looked at the Lord Kelvin display. And so Lord Kelvin essentially said, when you can measure what you are speaking about and express it in numbers, you know something about it. Okay? So a theory is fantastic. It gives you guidance. But until you can go into the laboratory, connect something up with wires, make the measurements, and come up with a set of numbers, then that's when you know that you've got something. And then, of course, what you should do with your theory is you should make sure that your theory gives you exactly those same numbers. All right? So, let's continue. So this is my commentary on the interaction between theory and experiment on almost all science today. So here what you've got is you've got your theorist who says, go into the lab and confirm my theory, or I'll have to do another calculation. All right? Then here's the experimentalist with the only tool that he knows how to use right here. He says, okay, but what do I measure? I only know how to use one instrument. And this has been the state of not only this field that we're in, but it's been the state of practically all of science for decades. And it's what's slowing things down. So what I'm trying to encourage, and what I'm trying to do, is encourage more dialogue, more discussion between theory and experiment, and encourage people to try to learn each other's language so that we can actually work together meaningfully. So, before we can even talk about edge of chaos and excitability, which are supposed to be the main messages here, I first have to talk about entropy production minimization. And what the heck is that? This is Brian Ridley. Brian Ridley is one of the greats of thermodynamics and also electronics. He was elected to the Royal Society of Engineering in 1994, and this is just extracted from his biography. And what you'll see here is that from the physics side of the world, everyone thinks that Brian Ridley did everything interesting there was to do about negative differential resistance. If Brian Ridley didn't do it, it didn't exist. A little over the top, but the fact is that Brian Ridley did understands a very important aspect of negative differential resistance, and he was the first to describe NDR instabilities in terms of propagating dipole domains in current filaments. So here is his paper, 1963, Specific Negative Differential Resistance in Solids. And what he did was he showed that any material system where you connect some wires to it, and it is, in this particular case, we'll talk about current controlled. If you start to run a current through the system such that it shows a negative differential resistance, the system will actually collapse. It will go through a bifurcation, which is thermodynamically controlled, has nothing to do with nonlinear dynamics. And that system, what it will do is it will jump spontaneously down to a point of much lower entropy production. And what that means is a much lower voltage. So if you sort of, and I'll show you some plots later, what you'll see is you'll know the signature, like the signature of a memristor is a pinched hysteresis loop. The signature of a Ridley transition is a sharp drop in the voltage versus current in a system. All right? And so, but there's something else here that Brian didn't actually realize at the time. When you have this transition, when you have a Ridley transition, the system has essentially gone to a state of optimum thermodynamic efficiency. That's what drives it. And so when this natural force, if you will, of entropy production minimization, which means it gets as close as possible to equilibrium as it can, but it's not at equilibrium because it's got current flowing through it, you actually you're at the optimum thermodynamic efficiency in the system. And for him, that didn't really matter because he was just thinking about NDR and making a larger NDR. But for us, when we're talking about devices and circuits and systems, what this means is that once you've gone through this Ridley transition, whatever you've got is as good as it can possibly be thermodynamically. You are given the gift of optimum thermodynamic efficiency, and it comes for free. All you need is a system with negative differential resistance. And so what this does is it sets the table for edge of chaos. This is what essentially enables edge of chaos to do what it can do. So this has actually not been around for a very long time. The first observation of this abrupt decrease in voltage for a system that has a negative differential resistance was in 1936 by, well, here's a familiar name, Walter Schottky. All right, so before there was a Schottky barrier, there was this, which was puzzling, but being Walter Schottky, he actually came up with the correct explanation for it. And the explanation for it was that what's happening here is that the current density in his device that he was looking at concentrated down, formed a narrow hot channel, and that was accompanied by this drop in voltage in the system. So the Ridley transition was observed, almost 3 decades before Brian came along and rediscovered it, if you will, and looked at it theoretically. But the problem is that Brian never wrote more than that one paper. The entire field dropped it. And there were interesting reasons. Let's see if we get there. So here is an experiment that we did in my lab during COVID times. And what we showed was that indeed you can have a system here where I'm essentially sourcing current into a simple memristor device and measuring the voltage. And what you see is there's a region of positive differential resistance where the voltage is increasing monotonically with the current. But then there is this point here and a very sharp drop in the voltage and simultaneously in the power, and simultaneously in the current, the entropy production. So this is the signature of a Ridley transition. And I'm going to show you this over and over again. Practically everything has it, if you know how to look, if you've got the right instruments, if you're making the right measurement. All right, so here's just a set of 4 such Ridley transitions. So here's the Mott transition in NBO2, and you can see that this transition, there's a sharp transition here, but it's not very deep. And so NBO2 turns out to be a material system where the Ridley transition is not very large, and it also turned out to be the first system that most of us looked at. And so we were able to fit the voltage current curve with a somewhat smooth curve and ignore or not even really realize that the Ridley transition was there. But then when we got to VO2, there is a very, very sharp Ridley transition, and you cannot ignore it. Lanthanum cobalt oxide, which actually has a totally different conduction mechanism from niobium dioxide and vanadium dioxide. This is called a spin transfer material. So it doesn't have a first order phase transition, doesn't have a Mott transition. It just changes around the number of spins in the system, but it undergoes a very sharp and steep Ridley transition. And this one actually has a hysteresis associated with it. And then here's another interesting one. This one is silver in silicon dioxide, and Stefan, you're going to do a model for me on this, right? You're going to compute this this type of system, a filamentary system. But this is a diffusive memristor. This is a silver ion drift diffusion, very similar to biology, but it also has a very distinctive Ridley transition. So many different types of systems. This is ubiquitous. This is a thermodynamic effect. And so anything that has a current-controlled negative differential resistance to it should display this effect. And everything I've looked at does. Now, what's the big deal? The big deal is that if you have a system, if you had a system which did not have a Ridley transition, this is what the voltage versus current plot would look like. It would come up like this, be nice and continuously differentiable, and the region of NDR would be fairly gentle. So the magnitude of your NDR is small, which means that the ability for the system to amplify signals is also small. And this is as good a fit as you could do to a system using what I'll call generic material capabilities. And the reason is that this is done using a lumped model. So in a lumped model, the current is flowing uniformly through the system. And because of that uniform current flow and associated uniform temperature in the system, you cannot get a sharp transition. Whereas when the Ridley entropy production minimization comes along, boom, you get a very sharp transition. It's a dynamical transition. It's not like a first order phase transition in a system. This is a completely non-equilibrium phenomenon. It doesn't occur if you just heat something up on a plate and monitor it. This occurs because you're driving current through the system, and the system wants to decrease the amount of entropy it produces. All right? So this is what you would expect. This is what you would guess. But this is what you get. How am I doing? Can't see a thing. Okay. And it turns out that this is very easy to observe. We're actually working now on I'll call it a fairly sophisticated theory to be able to go in and compute these Ridley transitions in good detail. And what's coming out is that there's all sorts of secondary observations that we're seeing in terms of currents and charge that Ridley predicted in words, but no one's had a chance to measure yet. So we're actually seeing this stuff. We're measuring and looking at these systems. And here is a very simple one. You can actually see a Ridley transition using COMSOL. So in COMSOL, you can essentially take a system which has a uniform material in it. In this case, it was the constants that we're using are for vanadium dioxide. And by increasing the current that's supplied to the system, what you'll see is that the voltage is increasing and the system is heating up. And because of there's boundary conditions, the heating is more in the center than it is at the middle. But then you get to a point here, a critical current, which is at the top of the NDR curve, all right, where if you just perturb the system a little bit, for instance, in this little square here, if you just change the temperature in that little square by 1 degree, even in COMSOL, which has no intelligence in it whatsoever, the system will essentially collapse. Almost all of the current goes into this one little narrow channel, so you can see a Ridley transition in a very, very simple type of simulation. All right, so now, after all of that, and what the heck time is it anyway? Well, that's about all right. So now, after all of that, I get to the main course. Right? We've just had our starter. Leon, of course, was on a parallel track. So Brian Ridley discovered entropy production minimization and went down this path. And essentially, most physics departments were following him. And then his work just kind of petered out because he got bored with it. And so, there was one major paper and a few other things. People like Ilya Prigogine and Rolf Landauer tried to work on it, and they couldn't get any place. And so the whole thing just kind of petered out. But then on the other track was Leon in nonlinear dynamics, and he got on his track, and 500 papers later, or whatever it is, he's made a tremendous amount of progress. And so this is where we're going to go. And so what we're going to try to do is we're going to try to understand a little bit more about edge of chaos from the point of view of some poor applied physicist or material scientist who's in the lab with a bunch of wires and maybe a simple voltmeter or something like that. I mean, how do you explain edge of chaos to some poor person who just needs to go into the lab and wants to measure something. All right? And what I guarantee it's not is it's not a Nyquist plot. So we've got to come up with something different from Nyquist plots before the experimentalists are actually going to be able to do anything with it. So edge of chaos is a state of maximal complexity between perfect order and complete randomness and is the origin of all complex phenomena, including, okay, well, can we measure this? What did Lord Rayleigh say? Right? If you can't measure it, if you can't put a number to it, it doesn't exist. So what I'm going to do is I'm going to show you that, yes, you can measure edge of chaos. It's a property of matter. It's sort of like superconductivity. Some materials have it, some don't. But you can measure it, and you can, and it's relatively simple to do. And very easy to understand once you know how to do it. Okay. So this is the paper. I talked about this last year, but this is the paper where Tim Brown and Suhas Kumar and I spent 2 years reading Leon's papers over and over and over and over again. And then all of a sudden it was like, holy, this is what it means? And so what we did is we wrote a paper to translate from the very sophisticated math that Leon talked about yesterday, where he had a list of like 9 theorems that you had to know in order to be able to define edge of chaos, and in which, you know, there's maybe 5 people in the world who can actually understand that. And we translated it into something that anyone in this room can go into the lab tomorrow and do a measurement and figure out whether you've got edge of chaos or not. All right? So, what is local activity, first of all? This is the main theorem. Local activity is the ability of a circuit element to amplify small pulses or fluctuations. How can a memristor do that? It induces a phase shift between current and voltage, and that phase shift has to be larger than pi over 2. By the way, if the phase shift is pi over 2, then you have a memristor that looks like an inductor. And so you heard yesterday about Leon talking about the 1 Henry inductance in brains. Well, all of that actually comes from the fact that a lot of the memristors, a lot of the axons in brains essentially have their, you know, they're in a quiescent area, but there's still a phase shift of pi over 2 between their current and voltage. And so it looks like a lot of inductance, but there's no inductance. If anything else, this to me proves that the memristor truly is the 4th fundamental circuit element, because you can measure a phase shift. You can't do that in a resistor. There isn't any phase shift, okay? All right, so how can a memristor do that? So first I'm going to talk about a class of devices, electrothermal memristors, and those are the niobium dioxide, the vanadium dioxide, the lanthanum cobalt oxide, all these various oxides. And so you have a definition of a memristor. You have a conduction equation, the electrothermal conduction equation, where you have current is a function of, is the electrical conduction, which is a function of voltage and temperature, times voltage, okay? And temperature is the state variable in the system. And so by making temperature the state variable of the system, we've thrown open the door and we've invited thermodynamics into the room. And once the thermodynamics enters into the room, it dominates, okay? Because the electrical conduction is a function of temperature. Then there is the dynamical equation for the system, and that's actually something which is called Newton's law. This has been around for a while. So Newton's law essentially says if you've got a system in which there is both a source of heat and a sink where it can come out, you write the balance, the thermal balance, like this. The thermal capacitance times the time derivative of the temperature is equal to, this is the heat flowing out of the system, and that's the heat being produced in the system. So that's Joule heating. And what happens is that if you have a time delay between whatever is coming in, if you have a time delay between, say you have an oscillating current coming in, if there's a time delay between the current and the voltage, that gives you a phase shift. It's very simple, isn't it? Very easy to understand. I mean, you know, I'm not plotting a complex plane and worrying about poles and zeros and whatever else. I mean, this is just, you know, this is just easy stuff. Now, in Leon's world and in Alain's world and a few others, what you wind up doing is you wind up creating these wonderful equations, looking at you know, the complex admittance, and then coming up with equivalent circuits which are contain you know, pseudo elements, and this is great for a circuit theorist. But as a guy who goes into the lab puts wires on something and makes measurements, I have no idea what this means. None whatsoever. I mean, and seeing this, I can't understand, first of all, what material would I even measure? And if I have a material that I've measured and it isn't very good, I've got no idea how to improve it. All right? So let's translate. Let's take this mathematical formalism and turn it into something that everyone here should be able to understand. And that is essentially a Norton equivalent circuit. In this particular case, what we have is a coupling. So we've got we have the electrical conductance of my material, my memristor material, but then we have the thermal circuit. And the thermal circuit has a thermal conductance, it has a thermal capacitance, and what you're doing is you're pushing power through the system, and that power is creating a temperature drop. This looks exactly like an electrical circuit, right? And so you've got a thermal circuit over here, an electrical circuit over here, and actually in this particular instantiation for an electrothermal memristor, all of the action is over here on the thermal side. The only thing that's over here is the fact that the electrical conductance is a function of temperature. So everything that's sort of, that you really need to know is over here, and this is all driven by thermodynamics. And the way to show that is take Newton's law equation, and divide it by temperature. When you do that, what you get is the rate of entropy change in the system. So there's the entropy change in the system, and this is the total entropy, if you will, and it has two parts to it, and this is where stochastic thermodynamics has come in and helped make things more understandable. You have two parts. You have entropy flow. In other words, you're creating entropy in the system, it builds up, and it flows out. So heat flows out, entropy flows out. And this is essentially a kinetic process. This is controlled by the thermal conductivity. And it doesn't matter too much. What matters is this term over here. This term, current times voltage divided by temperature, that is entropy production. The larger that number is, the more entropy you're pushing into the system. And what nature wants to do is it wants to minimize the amount of new entropy that's being created. And so it wants to minimize this term. And so literally, what we've shown here is something that Brian Ridley and Ilya Prigogine and Rolf Landauer never really had. They didn't have a connection between the world of thermodynamics and the world of electronics that they were looking for. But here, with this particular type of memristor, we show this directly. All right? And so there's an extra step, if you will. Instead of just solving these two equations here, okay, if you want to know something about the memristor, you need to solve them with the constraint that this is minimized. And it makes a big difference. All right. Now, it turns out that because we have this duality between the electrical and thermal degrees of freedom, that edge of chaos and local activity can be even more dependent upon temperature than on voltage or current. So you can have a locally active memristor in which the resistance is essentially constant if you happen to have something that has a very large and appropriately signed gradient or temperature gradient of the thermal conductance. And so this is shown here. So when you understand this, now what you can do is you can start to make plots that look like phase diagrams. And again, everyone here should know what a phase diagram looks like. Maybe everyone, but Alon and a few other people, I don't know. So here's a phase diagram. And in this phase diagram, we are able to take all of Leon's rules for what is a locally active system and what is edge of chaos and what is passive. We're able to take all of his rules, apply them in the domain of real materials, and instead of just having a set of Nyquist plots and a bunch of rules that you've got to follow and worry about whether poles and zeros are wherever they are, what you do is you just plot put plots, little x's here, and you will know whether you're in a region which is locally active but not edge of chaos. You'll know whether you're in a region which is locally passive, or you'll know that you're in an edge of chaos region. And what's important to know is what is the gradient of the electrical conductivity and the thermal conductivity. And those are things that you can easily measure in the lab statically. So you can go into the laboratory, you can make static measurements of, for instance, electrical conductivity and thermal conductivity as a function of temperature. From that, calculate the derivative with respect to temperature. Now you've got two functions, divide one by the other, normalize by the difference in temperature, and now you are able to plot on this plot here and know whether your system is locally active or not, and never have to reference a Nyquist diagram or poles and zeros. Isn't this easy? It's not too bad. This only took me 17 years to figure out. All right. Now, there's one other issue, and that is most of the time when we're doing our experiments, we're actually looking at oscillators. We're interested in things oscillating. And so the way we do that is we add a capacitor in parallel to the memristor, our temperature-dependent electrical conductivity. And now all of a sudden you look at this diagram and you see that it's the dual of each other. The description of the heat flow and the description of the current flow are essentially the same. And you get very similar differential equations, and now there's two of them. This is the conduction equation for current flow. In other words, this is, or the other way of describing this is the capacitor equation. This is the dynamical equation for heat flow. So this is current flow, heat flow. You put those two equations together, and now you have an oscillator. Now you have a second order system, and the system will oscillate. There's a little side note here. And the side note is that there's this wonderful thing called Chua's riddle. And in Chua's riddle, what he talks about is you can have a system which is biased, locally active, a memristor, and it just sits there, it just looks dumb, it's inert. But if you then connect a passive element to it, it will start doing something interesting. For instance, if you attach a capacitor to it, it will start oscillating. Now, the problem is that most commercial instruments have all sorts of internal capacitances and resistances, and you have no idea what they are. And if you call up the manufacturer and you can say, please, Mr. Manufacturer, sir, can you send me a circuit diagram of the inside of your instrument? They will say, get lost. No, I mean, that's our intellectual property. You can't know what's inside of our instrument. And don't worry about it. Just plug it in, turn it on, and it's going to tell you the truth. Well, it doesn't. It lies to you. And the reason it lies to you is you can't know, they won't tell you what the internal capacitance and resistance of the system is. And because we're working with nonlinear dynamical elements, they couple into the circuit, and the behavior that you get out is completely unknown. I mean, what you're doing is you're using a black box to try to test a black box. And so you're stuck. You either have to do a whole bunch of calibration of your commercial instrument, or you build your own. That's just the truth. If you really want good data, you know, you have to be aware of the fact that nonlinear dynamical systems couple to external impedances, and you can't know the actual properties of the device without knowing that or without measuring it. That's another way of doing it. You essentially calibrate the system and you measure these internal impedances. All right, but it's a lot of effort. It turns out to be easier to build your own than it is to calibrate the existing ones. Okay, so just very quickly, I'm going to revisit vanadium dioxide. And so I showed you earlier that this demonstrates the Ridley transition, where you've got this PDR region, this abrupt drop in voltage, and that this behavior is accompanied by the collapse of the current density in the system, where you have a spontaneous symmetry breaking. You've got a region of very hot current density flowing in what is actually a uniform material. All right? But when we made these measurements here, when we made these observations, at the same time we were doing that, we had an oscilloscope attached to the system, and we were looking at these oscillations. Right? So most people, when they're playing with this, what they're doing is they're looking at this, and they say, oh, we got oscillations, isn't that great? But they don't know that this is going on. And it's always going on. It's guaranteed. So, so this is the issue. The edge of chaos essentially occurs where Ridley creates the capability for it. And what Ridley creates is a capability which is thermodynamically optimum. It's the best you can possibly get. So it sets the table for local activity. Now, how do you calculate this? Well, we're trying to do this very fancy connection where we're taking circuit model systems, circuit simulators, and connecting them with COMSOL in order for COMSOL to be able to calculate the IV curve and everything else and feed it into the circuit simulator. And that's really ugly. So we found a shortcut, and the shortcut is just, instead of to use one memristor in this circuit, use two. So use two parallel memristors. One of the memristors represents the hot channel in the material, and the other represents everything else. So you've got two different temperatures, right? So you've got two memristors, you've got two different temperatures. One's the hot channel, one's the cold channel. And it turns out that this approximation is extremely good. This allows us to, so here's experimental data that we measured from the oscillations of this system. And there are the model simulations. And so we're able to reproduce the dynamical data in terms of the frequencies of oscillation almost exactly with this simple model. There's some issues with respect to the amplitudes, which are probably a little bit understandable. But for a simple model, I mean, what this does, it recovers the niceness, if you will, of a compact model by putting two of them in parallel. And as I say, it works a lot better than it should, but we're trying to do better. But this is practically free. This just takes an existing compact model, and instead of using one memristor, you got two, and you know that barely adds any complexity to the model. Whereas what we're trying to do when we're connecting COMSOL with a circuit simulator, it's ugly, cumbersome, and so far it actually doesn't give anywhere near as good results as this does. Just Stefan, you're awake back there? Yeah. Okay. All right, so how am I doing? Now, we started a bit late, and so I'm going to go for just a little bit more, okay? So once we had gotten to this point, we realized that in our view, local activity and edge of chaos had been, I'll say, somewhat reasonably indicated in Leon's analysis of the Hodgkin-Huxley equation. But there could be arguments in those complex systems that it actually wasn't anything to do with edge of chaos or local activity. It could have been something else. And so what we set out to do was make a measurement on an inorganic system that would prove indisputably that this system was locally active and was in edge of chaos. And so that experimental issue is in this paper here, which is called axon-like active signal transmission. And this comes about because, of course, you know, the Hodgkin-Huxley equation really is trying to model the axon. And if you wind up showing that you can model the axon, you should be able to build one and then measure it, right? Go back to Lord Kelvin. You know, you can't understand something until you can measure it and put a number on it. So, axons transmit signals with high fidelity. Think about a whale. If a shark comes along and bites a whale's tail, there is a set of impulses that travel from that whale's tail 30 meters to its brain without distortion or loss of amplitude. Then it makes a decision, I'm going to knock that shark away, and those impulses go from the brain all the way down to the tail, without distortion, without losing amplitude, okay? And it's traveling through meat, right? Salty meat. Well, can't we do something similar? So let's give that a try. So the first thing that we did is we switched materials. It turns out that vanadium dioxide, for various reasons, has too much going on. There's too much interfering physics that confuses the thing. And so we switched over to lanthanum cobalt oxide. And then we made a very simple memristor, and we made measurements. But in order to make these measurements, we had to build our own power supply. And that's because this system wanted to oscillate if we used any commercial power supply, and we didn't want it to oscillate. We wanted to measure the native properties of the memristor without the oscillations. So we made a power supply for which the internal capacitance of the power supply was below what's called the critical capacitance for the memristor, and so it was like it had zero capacitance. Then what we did is we essentially mapped out the voltage versus current bias here. And so here you can see the region is positive differential resistance, there's a transition region, and then here's negative differential resistance. All right, this region here is passive. This region here, as I'll show you, is edge of chaos. And then there's a boundary between the two. And so what we did is we put a bias current on the device, then we added a little voltage signal, and we looked at with an oscilloscope, the time trace of the current and the voltage, and we could see that when we were on this passive line, on the NDR line, the voltage and the current were exactly on top of each other. When we got to the maximum of the peak here, all of a sudden the system shifted and the current and the voltage were pi/2 out of phase. And then look at this. Look at the noise in the signal. The noise jumps up. Then we went, so that's 1 milliamp, 3 milliamps. Then we went to 4 milliamps. And at 4 milliamps, the system separates out. And now you have a phase shift between the current and voltage of almost exactly pi. Now, all of these observations that I've just told you were things that Leon predicted. He predicted all of this by looking at his mathematical formulation that nobody else understood, and he was able to say from that mathematical formulation, this is how things should work. Well, me not being smart enough to do that, I had to go into the lab and spend years to actually do the measurement and show, indeed, this is the case. So yes, this is an experimental illustration or measurement of edge of chaos. It shows that it's real. Okay. Now, once we have that, we can say, well, where did all this come from? It came from thinking about Hodgkin-Huxley and axons. And so we actually built a very, very trivial and simple transmission line in which we put a bias voltage between the two electrodes in the transmission line. The metal lines are on top of lanthanum cobalt oxide. So by putting a bias current between the two, we were then able to inject a signal at one end of this wire here, and then measure the signal out the other end. And if we bias the system into the region of negative differential resistance, what we saw was that the output signal, V out, the output signal here was larger than the input signal here. So instead of the metal wire dissipating the voltage, it amplified it. And the amplification is happening inside the metal wire. That's interesting. If you bias the system in the PDR range, well, now things behave as you would expect. Now what you have is a gain less than 1, and the system is dissipative. And so if you plot this versus frequency, what you see actually is there's a very strong frequency dependence, because in fact you wind up creating a low-pass filter here. And so as long as you're in this lower frequency range, you get a gain of about 1.3, which was actually much larger than I could possibly dream. I was going to celebrate if we could have a gain of like 1.05. Having 1.3 was like, throw out the confetti. But it's frequency dependent. But all of this is known. And Alon gave a talk yesterday in which he showed some of these issues in a different way. So I've got one last topic, and I think I've got the time to do it. So here it is. It's coming, Leon. I'm going to talk about excitability. So I'm trying to get Leon excited, because I am, because what we've done is we've looked at a different type of system. And I've shown this to you already, but we've looked at what Joshua and I call a diffusive memristor, which involves the presence of metal ions and metal atoms in a dielectric, and you apply a current in this case, not a voltage. So we're not looking at a threshold switch. We're looking at a system that we're going to bias into edge of chaos. So we apply a current to this diffusive memristor, and what do we see? Well, this has become an old friend by now. What you see is that the output voltage rises significantly. It hits a particular current, a critical current, then all of a sudden the voltage just plummets in a sharp transition. So what is this? It's a Ridley transition. This is the signature of a Ridley transition. But what does it do? What it does is it gives you this region here of very steep negative differential resistance. This is the home for edge of chaos. So entropy production minimization creates the ideal place for edge of chaos to be able to do its thing, shall we say. We can take the same data and we can plot it not as voltage versus current, but as power versus current. And now what we can see is that the power actually decreases. And there's a region here which is the minimum power. And so this is kind of crazy. Here you have a device, and what happens is I increase the current, it comes up, but then the power actually goes down, and you get to this point here. And what's that point? That's the point of optimal power dissipation. So the place where this device dissipates the least amount of power and very closely creates the least amount of entropy is here. Or if I can get it's there. So you've power optimized the system. And you've power optimized it for what? Well, you've power optimized it, in this particular case, to be an oscillator. And so now what we have is a system which is guaranteed to have the most efficient oscillator that you can build using these components. Without doing any work. The only work that you do is actually turn up the current high enough to get into this region. Now, let's take a look at the voltage versus time characteristics for this plot under two regimes. One is essentially very, very low capacitance, where the capacitance is lower than the critical capacitance for the system. And the other one in which there's an intentional capacitance that is larger than the critical capacitance. So for the low capacitance, if you are in the region of positive differential resistance, you have this passive PDR. You just have a constant voltage, and if you look at this line, you really can't see any noise. If I now bias into this region, this pink region, the region of the Ridley transition, now all of a sudden, look at this. Now I'm in the NDR region. Look at the noise on this thing. Look at the noise on that curve. And it's astounding. I mean, you sit there and you tweak, you go, no noise, no noise, no noise, boom, noise everywhere. Well, this is actually, Leon predicted this. He says that, when you're in the edge of chaos, that system will amplify small signals. And so what it's doing is it's amplifying the noise. And when you see this, when I saw this, I started doing a little jig. I don't want to try to reproduce it here because I'm very clumsy, but what this shows is this is a visualization of excitability. This is telling you that when you hit this region of edge of chaos, this system really wants to do something. It wants to jump someplace, but it always comes back to its starting place. So it's trying to amplify a signal, but there's no signal there to amplify. All there is noise. So this is excitability, and you can see it when you have noise in your circuit. If you're working with a toy model with no noise in the circuit, you don't see this. You just have to say, well, this is excitable. But no, this tells you obviously that it's excitable. And then if you do the same experiment out here in this region, which is kind of interesting, this is zero differential resistance, where you, over a very wide range of input currents, the voltage is essentially constant. You essentially have an initial spike and then a transient that dies out in this region. Isn't that cool? Now, this is even more cool as far as I'm concerned. What we've done, Stefan, you're still awake, right? Okay. What we've done is we've modeled this using a model that Stefan so graciously cited yesterday. But we had to adapt it because the model was set up to be a model for a threshold switch, and we want it to be for a system with current input. And so we were able to model the PDR region, the NDR region, and the ZDR region. And essentially what the model says is that there's a bunch of little silver nanoparticles that form along an axis. And so this is giving us symmetry breaking for free. So we don't actually have to make some sort of a funny model with two parallel memristors, because in this particular case, in the ion case, the formation of a filament is driven by entropy production minimization. That's why all these stupid things that we have filaments. These devices want to minimize entropy production. And the easiest way for them to do that is to make a filament. All right? So here we have the various stages of filament formation. But look at this. I mean, this is the one that I'm going to point at. And so this is the voltage versus time experiment and simulation. And look at the agreement between the noise in the circuit and experimental and measured. You know, now this is, you know, there's some machine learning going on and some other stuff, and I'll admit that. But this is remarkable. But what's even cooler is we can look at the state variable. In our case, the state variable is essentially the length of the filament within the system. And the filament isn't necessarily continuous. But what you see is that the length of the filament is like 95% across the gap, the silicon dioxide, and it never wants to short. In this system, we've got a constant current applied to the system. This system is noisy as all get out, but look, it's stable. It does not want to short. It will not short unless you really crank up the current and just blow everything out. And you literally have to get out of the region of negative differential resistance and really push it hard in order to get this thing to short out. This thing is, this region here is a region of stability, but look how this thing is pulsing. Pulsing, 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 pulsing. So what the thing wants to do is not short out, it wants to blow up. It wants to open up these filaments. But by doing that, by opening up the filaments, what it's doing is it's trying to amplify voltage. So this is excitability. This is what Leon talks about in his papers. He said the key to edge of chaos and the key to all of these wonderful issues in these systems is the fact that you have excitability within your system, and that excitability is stored up energy, if you will. It's stored up excitement where it wants to amplify a voltage signal. All right, I can see that I'm kind of at the end of my rope. So what I want to do is just very quickly say that there's this issue of edge of chaos and excitability. Local activity is the capability of a system to amplify small signals. And you've seen that, right? I've shown that to you multiple times now. It's measurable. You observe it in the laboratory. And so an example of local activity is negative differential resistance. Edge of chaos is what we call semi-stable local activity. It's a measurable non-equilibrium material property. Many materials have it, many don't. It depends upon current and temperature. It's a dynamical property. It's different from the types of things that you think about. A circuit element in the edge of chaos is excitable. And I showed you that excitement, right? You can see it on your oscilloscope, on your, on your PowerPoint prize. And so, but you only see it in the presence of noise. So if you're doing theory and there's no noise in your theory, you're never going to see it. Alon, yeah, okay. And of course, this whole thing is necessary for spiking neuromorphic circuits and amplifiers and the foundation for computation, complexity, and adaptability. And I was just going to say, 3 years ago, we had two materials that we knew that had this property, the property of edge of chaos, vanadium dioxide and niobium dioxide. Then we got another one, lanthanum cobalt oxide. Then we had 3 and we celebrated. Now we have thousands. What we've done is we've gone into the literature, we've found electrical conductivities and thermal conductivities, we've calculated all this stuff up, and for a very wide range of materials, 28 out of an initial selection of 40 materials, we found that all of these things can be in edge of chaos with a wide range of frequencies and powers required and everything else. Now, they can all be in edge of chaos. Most of them aren't useful, but they can be there. But the other issue is that from this set, you can start making alloys. And so, by making alloys, now all of a sudden you go from a candidate base of 28 into the thousands. And then, of course, you add the diffusive memristor, which is a completely different type of animal, and all of the different types of diffusive memristors. So all of a sudden, our space of being able to work in has gone up, from being embarrassingly small to having only 3 materials. Now we have thousands, and it's hard to choose which one we're going to look at. So we have to do simulation. All right, so finally, what are the implications for circuits? Consider a cellular nonlinear network as an example. All right? If you have a cellular nonlinear network and each cell in the network is an edge of chaos, you have already guaranteed that your cellular neural network is at an optimum in its thermodynamic efficiency. Just by building it and turning it on without having to do any design parameters, any funky things, this system is already thermodynamically optimum. So anything you do with it, you actually can't do anything better with that particular material set. You'd have to find a different one. So that's the first thing. But the same bias that puts you in this region of thermodynamic efficiency is also the bias that puts you in the edge of chaos. It's the thermodynamic efficiency that creates this steep, friendly region that you can, in which the edge of chaos can live. All right, and I'm going to speculate that this convergence, this fact that these two different things, the ability to be thermodynamically efficient, thermodynamically optimum, and in terms of edge of chaos, be computationally maximal, happens at the same time. And this is a gift. This is a gift that nature gave us, and I postulate that this is why evolution was able to actually create these things in our heads called human brains. I mean, for evolution to have tried to optimize two different things separately, one to optimize the power dissipation or the entropy production dissipation, and then to optimize the computational capacity, that's an extraordinarily low probability event. But when those two things converge, or when they essentially occur and are the same thing, it makes it much easier. So, thank you, and I appreciate your time.